Okay, hi folks, this is video number 3 in a series looking at advanced higher past papers, and in this one we're looking at centripetal force. So let's go and find a past paper to have a look at, and we'll see what the question looks like. So we're going to start with the 2018 paper, and it's question 2. So question 2 usually covers rotational motion and centripetal force. So let's dive straight into this one. A student places a radio-controlled car on a horizontal circular track, and the car travels round the track with a constant speed of 3.5 meters per second, and the track's got a radius of 1.8 meters. And we have to explain why the car is accelerating even though it's travelling at a constant speed. Well, you should know that velocity is a vector with magnitude and direction, and if the direction is changing, that means the velocity is changing. Therefore, it is accelerating. That's for 1 mark, and the marking instructions are accepting either that the direction or the velocity is changing. Okay, part 2. Calculate the radial acceleration of the car. Straight to your relationship sheet. There's the relationship for radial acceleration. So it's v squared, that's 3.5 squared, over the radius, which was 1.8. Nice and easy. Standard 3 marker here, and you'll get an answer of 6.8. Watch your units. It's a linear acceleration towards the centre of the circle, the radial acceleration. 6.8 meters per second squared. And there's the SQA marking instructions, pretty much exactly what we've got there. And 2A part 3, we're told the car's got a mass of 0.431 kilograms, and the student increases the speed of the car to 5.5 meters per second. And the total radial friction between the car and the track's got a maximum value of 6.4 newtons. And we have to show by calculation that the car cannot continue to travel on a circular path. So if it's a show question, we have to start with a relationship from the relationship sheet, and in this case we're going to use the central force relationship, F equals mv squared over r. Sub in all the values that we know. So the mass is 0.431 times the speed, 5.5, don't forget to square it, divided by the radius, which was given in the diagram at the top, that's 1.8. And if you do that on your calculator, you're going to get an answer of 7.2 newtons. That is the required centripetal force. And that required centripetal force is greater than the maximum friction available. Or in other words, the friction is insufficient to provide the required centripetal force. And the important words there are required centripetal force or friction insufficient. And there's the SQA marking instructions, with 1 mark for the substitution into the central force equation, 1 mark for getting the 7.2 newtons, and the final mark for stating that the required centripetal force is greater than the friction, or that friction is insufficient. Pretty tricky, that last mark. In question 2b, the car is now placed on a track that includes a raised section shown in the diagram, and the raised section of the track can be considered the arc of a circle. So we've still got circular motion with a radius of 0.65 meters. Then we're told the car will lose contact with the raised section of the track if its speed is greater than a maximum velocity Vmax, and we've to show that Vmax is given by the relationship Vmax equals root GR. Now that relationship is not on your relationship sheet, so we're going to have to derive it from the fact that it's the weight of the car that provides the required centripetal force. So if the car's going really slowly, then the weight of the car will be greater than the required centripetal force. And the maximum velocity will happen when the weight of the car is equal to the required centripetal force. So mg equals mv squared over r. Now m will be the same on both sides, so it will cancel out, and then all we have to do is rearrange for v. So gr will be equal to v squared, and square root on both sides, then Vmax will be equal to the square root of GR, and that's what we were required to show. And because we're equating the weight with the centripetal force, we should really have Vmax written at each stage of the derivation there. There's the SQA marking instructions, 1 mark for showing both relationships and 1 mark for equating them and then showing it right through to that final answer. Alright, 2b part 2, calculate the maximum speed Vmax at which the car can cross the race section without losing contact with the track. So all we have to do here is use that relationship, Vmax equals root GR, and work out what that velocity is. So subbing in for G, 9.8 times the radius of the track, which is 0.65 metres, because it's a model car on a model track. And if you do that in the calculator, you'll get a maximum speed of 2.5 metres per second. And there's the MIs, only 2 marks there because you were given that relationship to start with. And then 2b part 3, a second car with a smaller mass than the first car approaches the race section at the same speed as calculated in b part 2. State whether the second car will lose contact with the track, and you have to justify your answer in terms of the forces acting on the car. So let's go back to our original derivation, which was that it's the weight of the car that provides the required centripetal force. But in this case, the weight will be less because the mass of the second car is smaller. But the mass on the right hand side will be smaller as well because the required centripetal force is smaller. In fact, those two masses are the same, they cancel out, same as before. And because the mass cancels out, then Vmax will be the same no matter what the mass of the car is, so for all vehicles. So the car will not lose contact with the track because Vmax is the same for all vehicles. There's the marking instructions, 1 mark for saying it won't lose contact with the track, and the second mark for the justification. The smaller centripetal force is provided by the smaller weight of the vehicle. Right, let's have a look at another centripetal force question and see what the similarities are, or more importantly, what the differences are. There's a huge variety of these types of questions, so let's have a look this time at the 2016 paper. And again, it's question 2, which tends to be where all the rotational motion questions are. So this is a horizontal circle here. It's a conical pendulum that consists of a mass moving with a constant speed in a circular path as shown in the diagram, and we have to explain why the mass is accelerating despite moving with a constant speed. This is exactly the same as the previous question. So same answer, the velocity is a vector, and because a vector's got magnitude and direction, then if the direction is changing, then the velocity is changing, therefore it's accelerating. And there's the MIs, so any one of those statements would get you the 1 mark. Then part 2, what's the direction of this acceleration? Well, it's towards the centre of that horizontal circular path. And be careful with your answers here. I would be a wee bit wary of writing towards the axis of rotation because that's a line. We really want to be saying towards the centre of the horizontal circular path. Anyway, 2 part B. Swing ball is a garden game where a ball is attached to a light string connected to a vertical pole as shown in the diagram, and the motion of the ball can be modelled as a conical pendulum, and the ball's got a mass of 0.059 kilograms. Then the ball is hit so that it moves at a constant speed in a horizontal circle of a radius 0.48 metres, and it completes 1.5 revolutions in 2.69 seconds. And we have to show that the angular velocity of the ball is 3.5 radians per second. Well, it's a show question, so we have to start with a relationship from the relationship sheet. It's angular velocity, so let's go for omega equals the angular displacement over the time, and we have to show explicitly what the angular displacement is. It's 1.5 revolutions, 2 pi radians in a revolution, So 1.5 times 2 pi will be 3 pi radians on the top line there. So in fact, let's show it explicitly as 1.5 times 2 pi over the time, which is 2.69. And if you do that in your calculator, you get the answer that we have to show, which is 3.5 radians per second. There's the MIs. 1 mark for showing an appropriate relationship. 1 mark for the substitution explicitly with the 1.5 times 2 pi. And don't forget to give the final answer exactly as it's stated in the question. Right, part B, calculate the magnitude of the centripetal force acting on the ball. Well, we're going to use the version F equals mr omega squared because we've just been given the angular velocity. So the mass was 0.059, the radius was 0.48 meters, and the given angular velocity was 3.5, and don't forget to square it in this equation, and if you do that in your calculator you'll get 0.35 newtons. That's a bog standard 3 marker for equation, substitution and final answer with the correct unit. Alright, question 2, part B, part 1, part C. This seems like a crazy way to label the questions, but it just means that they're all linked to the previous part of the question. So, the horizontal component of the tension in the string provides the centripetal force, and the vertical component balances the weight of the ball, and we have to calculate the magnitude of the tension in the string. So I think we need a right angled triangle here, where the hypotenuse is the tension in the string, and the horizontal and the vertical components are the other two sides. So we've got the weight vertically and the centripetal force horizontally. And we know what both of them are. The centripetal force we've just worked out is 0.35 newtons. So we can put that on the horizontal side. And the weight of the ball we can figure out from its mass. The mass of the ball was given right up at the top of the question. It's 0.059 kilograms. So 0.059 times 9.8 gives us a weight of 0.58 newtons. And then to find the tension, we're just going to use a little bit of Pythagoras, where t squared will be equal to 0.58 squared plus 0.35 squared, and the tension then will be the square root of all of that, which is 0.68 newtons. There's the MIs. 1 mark for working out the weight of the ball, 1 for doing the Pythagorean bit, and 1 for the final answer of 0.68 newtons. Then the string breaks when the ball is in the position shown in figure 2c. So the ball is going to then move off at a tangent to the circle. Oh, better read the question first. On figure 2c, draw the direction of the ball's velocity immediately after the string breaks. So it's a tangent to the circle. Make sure you don't go inside the circle. And that's pretty much exactly what it says in the marking instructions. So, two very different centripetal force questions. One was a conical pendulum. The first one was a horizontal circle with a little vertical humpback bridge. You might get a question on banking. It might even be a question involving the gravitational force or magnetic force. But the best way to see the sort of questions that are going to crop up then is to look at loads and loads of past papers. And again, I can't recommend highly enough Mr. Davies' interactive PDF, where he's got all the past papers separated into key areas where all you need to do is click on the hyperlink for a specific question that you want to have a look at. That's it for this one. In the next video we're going to have a look at rotational dynamics. It's usually question 3 in the paper, and that usually involves moment of inertia. We shall see you in the next one.